Hello, everyone. Just give them a second.
Hi, Emmanuel.
Hi.
Hello.
Okay, we're gonna start on the next presentation. This is Intro to Hacking from a newbie that started a week ago, and Kenny was probably more knowledgeable. This was for Tenchi, but he's not here. But the real one is this. Hopefully, to get you in the mood. That's you, Loudon.
Thank you.
Just as a last readme for me, interest just changed each week, so you guys know. I also love BSD.
Oh, okay. Do I have to go through the whole thing again? No, I won't. Second year CSEC major, CE minor. Low level, Windows, drones, cool stuff. Attempting to make air go burr. That's it.
Okay. So the way it's gonna work is I talk about what hardware hacking is, the protocol for talking to each other, and some attempt to get a shell on a hardware device. So a little backstory: in the time where I had to save the presentation session, I gave a talk about hacking Amazon. That was this cam right here. You guys can see it here. It's kind of broken now. At the beginning, I got this camera just for myself. I got the firmware from the vendor and just did some bin walk and extract the firmware, get the source code of the stuff using just static analysis, so nothing with the hardware. It was pretty cool because you got to see the file system and what a firmware looks like, but it doesn't really give you a full information about like what's running, like runtime, and like what processes and what ports are open. So to take that to the next step, we decided to do this, break it apart. You want to talk about this? I know you didn't write it.
Oh, okay. So this was previously OPSEC. It's not now. We used WYZE V3 cameras for ISTS. So like the original goal was to backdoor the cameras for scoring. With can I talk about the scoring thing? Yeah. So we had a terrible check using ICMP. That was funky as hell. We were trying to use RSTP, right?
Yeah.
Which is the actual stream that the cameras are doing, but we had no way of doing that because when we attempted to dump the firmware and re-upload our own custom backdoor firmware, it said no. An individual suspected that there was signature checking involved, but we couldn't really find out. So this is what we're doing now. We're actually backdooring at the hardware level.
Yeah.
Yeah.
And with that, we talk about what's hardware hacking.
Yep.
Again, I don't know much about this. This was just from a book I read, and a few days of just attempting to learn this. So I'm gonna sometimes mix some terms and just make no sense, but just forgive me. But hardware hacking is just you taking apart your device and just trying to extract every information you can from the chips directly. So that, like, again, serial ports, soldering, and all that fun stuff. The benefits of doing this is you can find like hardware vulnerabilities. Examples are
fault injection, balls. Why am I forgetting? Yeah, hardware level vulnerabilities, right?
Yeah.
We normally touch on a lot of software vulns, right? But we never really go lower than low, and lower than low is hardware.
Yes.
So yeah.
And
okay, so why is this important and relevant? It's cool, AF, very cool. Like I said before, hardware level exploitation is kind of ignored, especially by this club. I need to change that. CE, by the way. It helps when manufacturers don't publicly provide firmware, like in Emmanuel's cases where we got the firmware directly from the WYZE website. Yeah, a lot of vendors don't do that because they don't want people touching the firmware. I'm thinking, who doesn't do that? Can't think of any, but companies do that, right? Like I said before, getting lower than low-level languages can be really useful when we're attempting to break things. I.e., there's a video floating around on YouTube about a guy hacking into a crypto wallet and obtaining $2 million in crypto, right? You really wouldn't be able to do that unless you actually were doing hardware hacking, right? Breaking open the device and looking at it from a hardware level. So, yeah.
Oh yeah, and you can also have your desk if you're someone like aesthetic looking tables. You can have. It's kind of hard to see from here, but it's just your table full of just random electronic stuff. Pretty cool. I thought it was cool.
Yeah, aesthetical.
So when you get your device and you open it up, there are a few things you should look for. It's mainly the debug ports. It's just think of it like how you debug your code, where you put the breakpoints in the hardware level. There are some pins around it. There are a couple of them. The main one, or the simpler one, is the UART. That's what we're going to talk about today. When you're able to find those ports, you're able to, again, really simplify your development and just debugging in general. Also, it's there not just for you, but for the manufacturers. So when they're trying to fix stuff, they can easily just plug it in and just debug it. So this is the pretty much JDB for hardware stuff,
literally.
GDB or whatever. And the fun part about this is if you're able to just plug into all of that, you right away just get root. There's no, depending on how you do it, most of the time there is no password. You just get dropped into a shell in root. So it's not as hard as it sounds when you talk about hardware, but yeah. So I did say it's not hard, but there are some theories or definitions you need to know for this to properly make sense. The way you can talk to such devices with your computer is there's a protocol or a communication that has to be understood by both the devices. They're just called serial connections. And again, simple definition, just allows two devices to talk to each other via a serial bus. We're not going to talk about what that is because that's not what this is. This is just an intro. But the serial bus is something, you've probably seen it. Your USB port or your USB is a universal serial bus. So there are multiple types. But that's just a way for two devices to talk to each other.
Touch on the CAN and SPI. CAN is generally used in automotive applications. The CAN bus is a term thrown around inside the car hacking community. SPI and I2C are generally found in SCADA and in industrial control systems. And if you're an avid CTFer, you will have seen those challenges. Yeah, fun times. Okay, we're going to keep going. Okay, this is me. So although we use UART in this test, right? I did want to mention JTAG because in most applications and in most applications that you'll find, you'll be dealing with JTAG, which is named after the Joint Task Action Group. So like I said before, this is like an industry standard included on most embedded devices for excuse me. Oh my god, I'm choking. For most like engineers that want to actually debug their stuff, similar to like what Emmanuel said, it's used in the same fashion as GDB and Ghidra for looking at it after the fact and analyzing it in production, I guess. Yeah. So JTAG is used specifically for testing between two connections. So like I said on the PowerPoint, point A and point B using boundary scanning. We're not going to talk about that, but boundary scanning is implemented with that diagram on the bottom right. Some cool CE stuff that I'm not going to get into. However, it allows us to dump directly from flash and EEPROM memory. So like Emmanuel said, you literally just connect and you're able just to dump straight from memory. So you're able to pull firmware and look at everything runtime, right?
Yep.
And like I said before, although a lot of engineers enjoy including it on their products, they don't want people opening their products and doing hardware hacking. So they generally obfuscate the pins, normally not labeling them or putting the pinouts in random places all around the board, right? So who created this? I forgot. A person created this thing called the JTagulator, which literally just fuzzes the board to find the JTag ports. I intend on getting one of these and doing a little bit of router hardware hacking eventually. So we may see a presentation next year. But yeah, cool stuff.
There's a list of tools at the end that would be suggested if you really want to do hardware hacking.
Yep.
This is one of it. So he did the
JTAG stuff.
Yeah. I talk about UARTs because it's the simpler version of everything JTAG, else. UART just stands for Universal Asynchronous Receive and Transmitter. Again, communication between two devices. It can be in three modes. There is the simplex, half duplex and full duplex. The simplex is just one device just talks in one direction. It's just a one-way communication. The half duplex is they do talk to each other, but like one at a time. So just like a what's that thing you have, the walkie-talkie. Yes,
Oh,
that
yeah,
thing.
yeah,
It's
yeah,
a one-way, so it's you have to talk one, then you have to wait to get the response.
It can't be simultaneous communication.
yeah.
Similar to Ethernet, by the way. Yeah.
And there's full duplex, which you guys just mush of information. But the way the data is sent, there's a specific frame. Just like in our networking lab, there is different like standards for networking. There is a little bit for hardware stuff, for UARTs. So most of the UARTs are full duplex. So there's a need for a way to like synchronize the data. Because it is asynchronous, there is no like common time or clock to like know when to stop or listen, but there is a speed that needs to be known by both parties. A good way to understand this part is if you are talking at 480 and I'm talking about in 960 or 9600, I'm not going to understand what you're saying to me. In the hardware stuff, it's just going to be a bunch of gibberish. So the ASCII characters would not show. That's because they're talking on two different band rates, baud rates. So there, most times you don't know what the rates are, but there are some tools that will be able to help you like fuzz or find this data. Yeah, still talking about the frame itself. There are three parts for the UART frame rates. There is the stop and the start bits, the data itself, what you're trying to send, and the parity
Yeah.
bits, which is optional, not always used, but those three are required. If you're looking at this in a waveform, the high when it's idle, it's always going to be in the high voltage, which just marks as 1, so just a straight line. The more you send data, it'll go up and down. When it's lower, it means it's in the low voltage, which is you know it as 0. So 1 and 0.
Can I touch on this real quick?
Yes.
But going back to the baud rates, right? So this is a waveform, and this generally fluctuates from high and low based off of a clock, and the clock will generally be above this, right? If one device is let's say this is 4800, right?
Mm-hmm.
And another device is reading at 160, 100, whatever, right? It's 1,000, my bad. I can't count. These changes and fluctuations will be completely unaligned. So baud rate's important.
Yeah. In one of the books I read, it says that the most common config, so it is a configuration file, kind of, but the most config you see on most devices are 8 and 1, which stands for 8 data bits, no parity, and 1 stop bits. In the next slides, we talk about what each of them means. So the first one is the start and the stop. There's not a lot of information. It's just you send a bit to like tell the data that you send a start bit just to indicate that data is coming, obviously, and that changes the voltage from high to low.
Yeah.
So, and the same happens. Well, the opposite happens for stop, which it changes from stop to high. I did read there is a second. It could send a second stop bits. I couldn't find the reason why it would send a second one, but it can send 1 or 2, but usually 1.
Yeah. Like looking at this from a CE standpoint again, there's generally a circuit implemented on the chip that will detect the sequence of bits. So if only 3 are delivered, it's not going to start the transmission. So yeah.
Yep. So you get the start and the end. So the middle part, which is your data, what you're trying to send. This is usually between 5 to 8/9 bits, and that is always flipped. So in our reversing stuff, where we have the list significant bit in the front, it works in this case too. So if we're trying to send the letter S across from my device from the router to my computer, it's going to be something like this. It converts that ASCII character to binary, which is 101001. And in order to send, before it sends it, it has to flip that, flip the binary. So it becomes 11000100, whatever. And as you can see in the image, it just sends that over to mine. And the other device, obviously, if it's listening on the same rate, it would be able to convert each user bytes, so data bytes, to ASCII characters for us to see. This is one of the straightforward part of the UART frame. And the parity bytes is just used for detection. Again, it's really optional. So there are two parts of this. It is the even and the odd. An even parity is just the number of ones has to be even, and the odd, if it's odd parity, the number of ones have to be odd numbers. Back to that S example, if we send just like default, there's 4 ones in that S binary. So in that case, it's going to be an even parity because the number of ones are already 4, so it's even. There's no need to change. But if it is an odd parity, it's going to add an extra 1 at right there. It's going to add that 1 to make it even. Oh, sorry, to make it odd. So instead of 4 ones, it's going to be 5 ones. Again, really optional. Really, we don't deal with this a lot. It's just there. You want to talk about this one?
Okay, so like I was saying before, engineers generally kind of hide the JTAG stuff, but in our case, we were dealing with UART, so it was clearly labeled. Generally, when you're looking for UART, there's going to be a set of 3 pins, 3 to 4. In our case, it was 3, but generally 4 pins that are aligned, as you can see on the picture, and they're clearly marked. Sometimes they aren't. In that case, you would probably have to use a multimeter to determine the ground, and then from there you can go off that, or you can use a logic analyzer, which analyzes the digital signals of the transmit and receive ports. So
I think I forgot to say the way UART works. Do I even talk about it? Yeah, I don't. Sorry, just go back a little bit. The way UART works is you have to have 2 wires, mainly those 3 ports right there, the TX, RX, and the ground. Ground is always connected. Ground. Ignore that part. But the main part is the TX and the RX. The TX stands for transmit, and the RX is receive. And in order for the 2 devices to talk to each other, they have to be plugged into the opposite of the device. So if you're talking in TX, you have to connect to my RX, and my RX is going to be connected to your TX, and that's how it works. Not trying to be weird about it, loud in.
And also the 4th pin is power in applications. in applications.
Okay. Yeah. So.
No, I was just saying the 4th pin is generally power. In
power.
applications where VCC. In applications where the device can't be powered by an external power supply, it's powered directly through UART when you are debugging, right? But
if you guys don't, this is usually the 4 pins that are out there for UARTs. So, like I said, if it's not labeled, sometimes, like you said, sometimes all labeled, which is great because we don't have to do all of this, but sometimes it's not, so you have to do it yourself. The multimeter just measures the voltage and current, and Kenny talked about it, blah, blah.
No. We can, okay, so later on I'll actually talk more about the logic analyzer. We are going to have to use that because we had some issues when doing things, so Yes. Keep going,
The picture on the
my fault. I'm sorry. So on the left, there's a multimeter for measuring voltage and continuity, and continuity is just determining whether or not 2 points are connected to each other. And then on the right hand side, there's a logic analyzer, which is actually able to view the digital logic that's being transmitted. So as Emmanuel said, the UART protocol, well, not protocol, but the UART uses uses high and low bits being sent, and you're actually able to visualize that using the logic analyzer. So
and from there you can do, I think you can do a little bit of math.
Quick
it's
math.
pretty cool to see how it's being sent over. But with that said, it is a lot of
Is that like the same as an oscilloscope?
Well, I can't speak. An oscilloscope is analog. In our case, it's digital. Analog's a little bit different. they normally combine the two devices. Either way, they're very expensive and very cool. So, yeah.
Yeah, I just know that word.
Okay.
Analyzer could be like an automated process.
Well, it is in most cases. So it'll automatically convert the signal over to binary, and then from binary you can probably go into ASCII. Right?
Yeah. I've seen videos where it does it like on the
Yeah,
side.
it does
of
it on the side.
Yeah.
In my C labs, at least, it does it on the side.
Yeah. Any more questions before we move on? Okay. This is the other half of it, and this is where we take that theory stuff and try to, well, I try to implement it and possibly fail, which I did. But this is my process of trying to break into the WYZE camera at first. Before I even open it, I learned that every devices that use wireless has to be, well, they have a FCC ID, and then you can search for it on their website. Then I break the device, find the ports, connect to them, hopefully get root, and the rest of more firmware stuff. Like I said, FCC ID is required for every device that does wireless, and usually the ID is at the back of the device. In this case, it's right there, and you can just search for it. It would give you an information that looks like this, but I went through that and it was nothing exactly useful. So what I did was just look up FCC, or the company's name, WYZE Camera, and FCC. Then I found this, the second image, which just gives me more information. The most important ones is the internal pictures.
Yeah.
So this is just the manufacturer just disassembling the device themselves. So you don't have to know all this stuff. But the good thing about this is you're able to see what's inside before you break it. And right there, we can see the port even before opening the device. So now I know it's there, but the problem here is it's not labeled. So I need to possibly do my own multimeter and whatever to find like what each port is.
Also, back to like the obfuscation stuff. This is a requirement by the FCC to do for all like devices that use radio frequency, right? But like I was saying before, they're not required to actually label the chips that are on the devices. So in situations where you can have like I don't know why you would do this, but like a crypto wallet, right? You don't want your competitors knowing what chip you use to implement security, so they'll just like wipe the chip entirely. That goes back to actually like reversing and taking X-rays of the PCBs to determine what it actually is doing. So this is helpful in our case. However, in the future, it won't be. But yeah, I'm sorry. Keep going.
Yeah, all depends on the product you're
Yep.
doing. I would say we've looked at a lot of router stuff, especially the TP routers
TP-Link,
and TP-Link router, and I would say they are just an easy target if you really want to start.
Yeah.
They're so easy. They even label it for you. Like it tells you what's what. And also there's a lot of videos out there.
Yes.
So this is me on last Friday night. I did not watch a video about breaking this, so I just started chopping. As you can see, it came out, god damn it, came out really good. I had to use a plier to just cut through it. Also use a knife and stab myself while doing it, so that was also nice. But after like 2 hours of doing this, we were able to get this image right here, able to get the device out there and see the ports, and I was so excited because we're getting closer to victory, and I was able to understand what was in this picture, so that was a good start. But it gets really hard if you don't have the right tools, but if you have everything else, easy peasy. The next step is the serial, again, the ports. The image on the left is not mine. Since this is not a new device, people have done their own research in this and just reversed it themselves. One of the hacks we found on GitHub actually did pretty much all of this and made custom firmware based on what you want. And this is the whole process the author went through just to be able to create custom firmware. So luckily this guy labeled it for me because I didn't have a multimeter or whatever, so I didn't know what to do. I could have possibly just try each possible points, but I heard that's not always good because you could circuit or you can
Short the board.
short the board and just break stuff. I think I probably did. I don't know yet.
That is actually possible.
It is
Yeah,
possible.
keep going.
So I was like, okay, I don't, and at this point I didn't have like a UART to USB, which
The
will
FTDI to convert the USB to serial. Yeah.
yeah. So that would, this little red device, what in the picture, pretty much converts that UART information to my computer so I can easily see it and use my laptop as a debugger. So before I even found about that, I thought I could use my Arduino to do that magic conversion. I saw a video, I was like, a YouTube video, and it seems like it worked, but not in my case. Just nothing was working. So, and those little guys are like $5 on Amazon. So why not just spend an extra buck on this? So that's what we did, and we have a little shiny right here. You guys can't see it, but so. In theory, if you have all of it connected, it would work perfectly, and you would get something like this image right here, which is the camera just rebooting, and that's all the log messages from the device. There are multiple ways to like get this information depending on what device you have. This PicoCon, I think that's its own small device, and it has its own command line. You could use that one. But if you have Linux and Mac OS, there is the default command called screen. You can just use screen, a path to the USB, and the baud rate.
Yeah.
When you write this command, it will just show you that. If you're a Windows guy, you can just use Putty. Putty makes it really easy too. So this is where I was able to get throughout in the last few days. The problem is I'm able to get output, but I'm not able to send something back to it, and this is where we're trying to figure out like what the problem is. Maybe I probably short the board, or the adapter is not working, or I messed something up. But this is pretty much where I got. I was going to show a demo, but it's always fun. It's always good to solder the pins to the board, because so it doesn't fall out all the time. I don't know how to do that. I tried. It didn't go out well. Also, I didn't want to trying to be careful. I don't want to get banned by RIT, so wasn't able to really do it at the moment. So he's going to do it next.
Yeah. Can I talk a little bit? Okay.
Yeah.
No. Personally, I suspect it's a multitude of things. I think either Emmanuel didn't solder it in there correctly, so it was like a cold solder joint. And it just didn't make complete contact. Or these devices come from China, and like I'm not pooping on China or anything. However, these are just known to be like dead on arrival on occasion.
Yeah.
These are like mass produced. Or 3, the camera's dead. Like the trace probably scratched, something like that. I don't know.
It's alive.
Yeah, it's okay. Well, yeah, it's alive.
Yeah.
So I'm gonna probably take it, or we're going to take it to the CE lab and use the logic analyzer and see if we can actually see the keystrokes being pushed to the camera. Because if we're able to determine that they're actually being transmitted to the camera, then, wrap it up. We know it's not our problem. And then if that doesn't work, we break open another camera and we do it again. You know the vibes.
Yeah.
But yeah.
But like just from like being able to see just log screen, we can see at least some really important information.
Yeah.
Like first, there is a part that shows like a command input, so we can see that it's doing some possible command injection that we can possibly inject into.
Yeah.
But that's one part of it. But the important part, like when looking through it really carefully, I did see this part where it says verifying checksum. So maybe the person that told me that there was a check on the firmware is probably right, because it says verifying checksum. So that if we do get everything to work and log into this camera when it's plugged in, I think the next step would be trying to look into that checksum part of it and see how we can either bypass it or just ignore. Yeah, a lot of possibly, yeah. We don't know yet. We're just gonna assume it's firmware or something else, but it is something recurrentize. It says. I just stated that process. Got somewhere, but didn't really fully get it. I would point out that this person right here. I'm just gonna close this for a little bit. Okay, we're gonna click on this. Sorry, just goes. I want to do some actual engagement. But so this is not the first time. This is another person who I've done a lot of research on it. I pretty much kind of follow. It doesn't really have like detailed instructions, but like it's good to just look at this. But just looking at it seems like in order to get full access to it, there are some modifications that might have to be done. especially to the bootloader. In this case, we have to edit the bootloader to run in shell after doing all its setup and all that stuff. Just this command right here. I think we don't use this in Red Team, but this is a trick we use for like networking live. When you get locked out of your computer and you don't know your password, you can just edit the bootloader to run shell at the end of it. So something we can do for this little device here. And there's a lot more information about like dumping the firmware, modifying it, and all that fun stuff. Hopefully when we get this part to work, we want to do that other half of it and do more. So yeah, that's where I was able to get in the one and a half week I had with this hardware phase of my life. I would say I got 60% done. That's good enough for me. Move on to the next project. But I would say, so far there's a lot of cool stuff that is just with this. If you really want to start, there are a lot of articles out there and YouTube videos. But this is just a list of tools that are going to be useful if you're thinking about like switching to hardware stuff, which I highly suggest. Let's make this cloud more hardware and software rather than just software. But these are some of the tools. The UART adapter, which is that little device right here. Again, pretty cheap, like $5 for 2 of them. There's the logic analyzer. Kenny has talked about it.
Yeah.
Multimeter, soldering station, look aesthetic. Have that huge mess on your table. Beautiful stuff. Also, you might need your brain for this because maybe a little bit of CE theory actually. Know how circuits works and all that fun stuff. So there's a lot of devices, but I think it is possible to do most of this by just a Raspberry Pi or Arduino. It's just going to be a lot more work.
Yeah.
But if you want to be fancy and you have a lot of money, you can buy a lot of devices for this.
It's definitely helpful to have a lot of like the debugging and just lab equipment in general. However, you don't need that. When I've interacted with serial devices and just microprocessors and microcontrollers in general, I've only had like the FTDI adapter / UART adapter in my laptop and soldering station pretty much. So you can do a lot with a little.
Yeah.
When it comes to hardware. Yeah.
Yep. So it's a small LB that you can spend a lot or spend little depending on what you really want to do. And the 2 big resources I would say that at least got me started. The first book is a practical IoT hacking book, which I read it in a 6-hour drive, and I was able to like pretty much where I got all of this information from. So if you're stuck in a 6-hour drive with your friends, just read a book. And you're an expert in that. You read for 1 hour. You read for 30 minutes, take a nap, wake up again, and just do it over for 6 hours. But the IoT hacking and hardware hacking, those 2 books are really, I would say, are the best way to start. There are YouTube videos. The third link is just a video about UART, which just gives, if you really want to know more about that protocol or device, it tells you about it. But I guess the big one is the last link, which is GitHub, which has a link to other stuff, the awesome book of IoT and embedded devices. I just found it. I'm going to take a deeper look, but I'm pretty sure it's going to be really useful for any sort of, again, IoT embedded stuff. Have anything to say?
Alternatively, you can get a major in CE or EE, which also helps this. I was also going to include the Ben Eater is a great resource for like learning just hardware stuff.
Yes.
I'm pretty sure he covers a lot of like the CRC and the serial communication, and even when it gets down to like actual like what the components of the devices are doing, like logic gates and what goes into these embedded devices. Great, yeah.
Yes. I would say after doing this, I'm thinking of doing a master's in CE, so
embedded security.
you never know. I have time to think about this. But to finish up, this is probably the last time you see me, so I'll see you guys in 2023, and the presentations will be passing to this guy, so he's gonna catch up, and that's it. That's hardware hacking for you guys. Hopefully you guys do more of that, which you should.
We will be.
Okay.
Oh, we will be.
Okay, so that's it for us. Any other questions about this?
No.